Hello everyone, in this video let us understand BJT biasing, that is collector to base bias. In the previous video we have seen fixed bias circuit and how the biasing is done. In this video let us see the collector to base bias technique. In collector to base bias technique, here the DC base bias voltage is derived from the collector voltage, that is VC. You can see here, compared to the fixed bias circuit, the only change here we can see is that this RB is connected to VC point. Suppose if you consider this as a collector terminal and voltage at this point is VC, we are taking the bias voltage, that is in between the base and emitter. If we are going to take this as VBE, this will be generated by using VC. Other than directly connected to VCC, here we are generating this VBE using VC. That is what the name says, collector to base bias. By using this VC, we are going to keep this IB as constant by choosing RB a suitable value. And now this becomes forward biased, and you can see this is N terminal, this is P terminal, and this is N terminal. Collector to base should be reverse biased. Collector terminal is of N type and it is connected to positive voltage, so that it is reverse biased. So forward biased base emitter junction and reverse biased collector to base junction make this transistor to operate as an amplifier circuit. So here the base resistor RB is connected in between the collector and base. That is the important thing. The advantage of this collector to base bias over the fixed bias is that this circuit improves the stability of the amplifier, where even if beta changes, there will be stability we can expect from the amplifier. So let us understand the analysis of this. Again we are going to apply KVL to the collector to base circuit. You can see from VCC to VC and then to the base of the transistor and to the ground. We are going to apply the KVL in this path. We can say VCC minus, here is the total current IC plus IB, which is mentioned here. You can see why, because the collector current is splitted as IC and base current is splitted as IB. So here the current generating here is IC plus IB. So while applying KVL, we need to take VCC minus the voltage drop over here across this resistor is IC plus IB into RC, minus again here one more voltage drop IB RB, so minus IB RB. Here is the voltage in between base and emitter VBE, so minus VB is equal to 0. As we know that IC is equal to beta times IB, in place of IC I am going to write beta into IB, and after simplifying I am going to get VCC minus beta plus 1 into RC plus RB into IB minus VB is equal to 0. Here we are trying to get the expression for IB finally. How we can find out IB here is that VCC minus VBE divided by beta plus 1 into RC plus RB. This is the expression for IB. So similarly we need to get the expression for IC and VCE, in between the voltage from here VC to emitter, that is VCE, we need to find out. So let us apply KVL again for this loop. Means VCC through RC, then to the collector terminal to emitter voltage. And easily we can write IC as beta times IB. Whatever the expression we have in IB here, if you multiply this with beta, that becomes IC. Now let us apply the KVL to the collector to emitter circuit. We are going to get the expression as VCC minus IC plus IB into RC minus VCE over here is equal to 0. From this expression we can get the expression for VCE. This is VCE. VCE is equal to VCC minus IC plus IB into RC. By using this expression, again we can go with the output characteristics and we can find the operating point, and we can fix this IC as well as VCE. This is all about the collector to base bias. Here we need to understand the collector to base connection. From VC point we are generating VBE and we are making this IB constant. In the next video let us discuss voltage divider bias. Thank you.